4, 6, 8, 10, 12, 16. If we wanted to know where the number 84,500 fit, we could mathematically calculate it. Here you go. Hey!
Wow.
83 seconds, it says. So if we knew what the numbers were, we could calculate their offset, which would be a lot quicker, right? I mean, to be quite honest, we can only do one mathematical formula and then boom, we're at the answer. That's even more efficient than the binary search, right? Because the binary search is giving us a big O of log n, where this would basically just be giving us a big O of 1. That would be much more efficient, don't you think? It's probably as efficient over the top of the binary as the binary is over the top of the linear. So, that's where we got to go in order to get more efficient. Because log n is pretty efficient. So now we're looking at something that's going to approach big O 1. That's where we want to be. So if we want to be at big O 1, we got to start doing something in order to get there. So in order to get there, we've got to actually involve math in our decision as to how we get somewhere. And that's what the abstract data type hash table is all about. It basically sticks things into a table or an array and based on a mathematical formula. And that mathematical formula has to work bidirectionally. You have to be able to use that mathematical formula to get data into the table and to get data back out. All right. Some terminology as far as hash tables are concerned. One of the biggest ones is if a hash table looks like this, this guy here is called a bucket. Now, in order to calculate which bucket we want to use, we're going to have something called a hash function. Once we get there, we have some things that could possibly happen. So let's say that we have this, and this is 1, 2, 3, 4, 5, 6, 7, 8, 9. Let's add one more. Just for the heck of it, we have 10. Here's our hash table. It's got 10 buckets in it. Now, we want to insert numbers into here. So in order to insert them, a very simple hash function could just be number mod table size. So our table size is 10. So anything we put in here, it would mod it by 10 and stick it at that location in there. So if we wanted to put the number 333 in our table, it would go right here. If we wanted to put 589 in the table, it would go here. Make sense? It's pretty straightforward. I mean, now we have this mathematical formula. We just apply that and we're all good to go. Everything just fits the way it's supposed to, and yada, yada, yada. All right, so there's a problem though, right? What happens if the next thing we want to put in here is 413? Where's that going to go? Same spot as the 333, right? Yeah, that's a collision. So if two pieces of data, complements of our hash function, want to occupy the same bucket, that's a collision. So now that they've collided, we need to resolve this problem. And what happens is we probe the table to find another location to put this in. Probing comes in a whole bunch of different flavors. One of them is linear probing. Linear probing says, okay, we'll just use the next one in line. That's linear probing. Another pretty common one is quadratic probing, where we basically multiply it times itself as we go forward. So what would happen, we're linear, we'd go 1, 2, 3, 4, 5, and quadratic, we go 1, 4, 9, 16, 25. That kind of deal. Now, once we fall off the end of the table, we just wrap back around to the beginning. Everybody with me so far? Now, for what it's worth, this guy is called open address hashing. And here's your important tip of the evening. I can guarantee you that this one will find itself someplace on the final exam. Say.
With.
No, the one I underlined. Pay attention. All right. So this is open address hashing. Now, one of the things that happens is that without collisions, so a non-colliding big old one. Woohoo! So I guess we just want to avoid collisions. And we're done, right? Takes care of everything? It's not that easy, right? So, but once we collide, what happens? If we're using linear probing, we start to take on a linear characteristic, right? The idea is we don't want this to become linear. We want our hash function to be good enough so that we don't have collisions. And if we do have collisions, we want them to resolve as quickly as possible. Now, one of the things that's a bigger problem here is what happens if the next number I want to add to this is 634? Where does that go? But number 4 is busy, so we have to put it here if we're using linear probing. So, not only do you have problems with your own data if you collide, you could potentially have problems if you run into somebody else's data. This is why we have quadratic probing. It basically gets you away from the scene of the crime as quickly as possible. Because what would happen here is with that, if we tried to put that here, we'd try here, then we'd try here. So you move very quickly away from there. One of the things that you want to avoid is this particular thing here, which is called clustering. Also sometimes referred to as clumping, like cat litter. Bless you. Twice. And so clustering is a bad thing because you remove a lot of the benefit of the hash table by virtue of this data all sitting right next to each other. So what we've come up, what we need to talk about right now is that hash tables can be insanely efficient, but they require you to understand the data you're putting in them. And if you understand the data that you're putting in them, your hash functions can become much more complex to help the data be distributed evenly across your hash table. Now, we do this because clustering adds a linear component to your hash table. So you don't want clustering. And if you look at this at the meta level, what you certainly don't want to see is if you're looking at something and you see things like this, right? There's a whole bunch there, there's a whole bunch there, there's a whole bunch there. This is indicative of a malfunctioning hash table. It's not going to be as efficient as it can. So sometimes you'll actually see hash tables where they'll hash twice. Once to get you the first location if there's a collision, they'll hash on secondary data to get you away from there. So that probing function actually is a whole other hash function in order to get you away from there. Typically what you're going to see is linear and quadratic are the big players as far as probing is concerned. Secondary hashing occurs quite a bit. But the problem with this is it requires your data scientists to come up with hash table algorithms that are going to build you non-clustering hash tables. Make sense? That's pretty much everything there is to know about hash tables. A couple more things, which aren't really necessary to know, but are good to know, is that here we just stuck integers in here. Typically what happens is you put a key into here, and the key fits into a data structure. So let's say we build a data structure that has, someone's name, phone, email. And we'll have another field in here, which is the key. What this allows you to do is it allows you to have somebody say, put this object in there, and I want you to use this key. So where this is an array full of integers, we can actually build something that looks more like this, right? Where this is some abstract data type over here, another one there. But the key is what we hashed on to get us to this individual location. So hash tables can be self-policing, determine their own hash function from the data that's passed to them, or you can pass a key in that you want to use in order to do this. So you can look at this and go, oh, well, as far as this guy's concerned, I could have just hashed off the first letter of the name, third number of the phone, and fifth letter in the email address. Subtract them all from capital A and create your hash table index by doing that. And that's the downside to a hash table, is you really do need to understand the data that you're dealing with. If you don't, you're not going to build an efficient hashing algorithm. So, with the open address hashing, one of our big things is we're trying to get this to be as efficient as possible, to be as non-colliding, highly efficient probing as possible. If we don't collide very often and we're very good at getting away from the scene of the crime, it's a pretty good open address hashing tool. What if we decided, well, the heck with it. Why don't we just embrace the linearity of a collision? So, yeah, we'll build a hash function that comes out to be as efficient as we possibly can, but screw the probing. Instead of having something that looks like this, why don't we build something that looks like this? use a hash function to get us to a bucket in the hash table, and at that bucket, just have a linked list there. So what happens? We're just embracing the linear component of the hash table. But, wow, it's a lot easier, right? We only have to worry about the one function. Once we get that done, if we have a really good hash function, then we just have this linked list here. There's a problem with linked lists, though, right? They're serial by nature. You could sort data in a linked list, but it doesn't buy you anything. But you can do some things like least recently used, most recently used, that kind of thing. So if we want to do least recently used, what we would do is make this into a stack. So the least recently it's used, the further away it gets. When we use it again, we can move it up to the front, that kind of stuff. And there are different ways to try to address that linearity of this linked list. It could be a queue, it could be a stack, it could be different things like that in order to build something that helps. This is called chained hashing. And that's really all there is to it. It's just a hash function, takes you to a linked list. Once you get to the linked list, you can decide. It could be a stack, could be a queue, you could do binary trees off of there. Another thing that you can do is that, and this is important to think about when you're thinking about abstract data types and whatnot. Odds are you're going to build very few pure implementations or something. You might build a pure queue because those are used very frequently for sequencing, first in, first out. But you're going to build a lot of data structures that are hybrids. So in this case, this is a hybrid, right? And this is a hybrid of open address hashing and a linked list. You could even say that, once I did this, what if I decided I had a hash table here, and off here, I have another hash table? Sure, why not? You can do whatever you want. Whatever happens to work well for your particular data. Characteristics that make really good hash tables are sparse data. Right? I mean, if all your data is really tightly clustered, then, okay, you've got to come up with a hash function that separates that data. One of the things also is that you want your hash table to be bigger than the data that you're trying to put in it. Because once the hash table is full, ooh, wow. You thought that resizing an array was tough. Resizing one of these means there is no way to resize this without remanufacturing the hash function. Because the hash function calculates a location based on the size of the table. So you actually have to pull everything back out of the table and reintroduce it to a new table in order to solve a hash table full. So typically it's not a very memory efficient thing because you're going to have a lot of unused space in order to make sure that you don't end up in a situation where it fills up. Because it fills up, it's painful, really, really painful. So make sure that your table is big enough to hold all your data and then some. When we start looking at quadratic probing, and we take a look at something like this, all right? 3, 4, 5, 6, 7, 8, 9. 10 locations. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Let's say we end up at 4. And then we start linearly probing. We go 5, 6, 7, 8, 9, wrap around 0, 1, 2, 3. That takes full and neutral. Quadratic, we would go 1, check here, then we go 4, right? Because 1 times 1 is 1, 2 times 2 is 4. So from here, 1, 2, 3, 4, we check here. Then we would go after 4, we go to 9, 4, 5, 6, 7, 8, 9. Then we go to 16, 10, 11, 12, 13, 14, 15, 16. Then we go to 25, 17, 18, 19, 20, 21, 22, 23, 24, 25. Then we go to 36, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36. We collided. Then after 36 comes 49, right? So 36, 7, 8, 9, 41, 2, 3, 4, 5, 6, 7, 8, 9. Hit that again. Then comes 64, 50, 1, 2, 3, 4, 5, 6, 7, 8, 9, 61, 2, 3, 4. Hit that one again. Then comes 81, right? 5, 6, 7, 8, 9, 71, 2, 3, 4, 5, 6, 7, 8, 9, 81. Hit that one again. Huh. Doesn't seem to be helping all that much, does it?
You know, the divide formula for quadratic program.
Huh?
Quadratic program. What's the formula is multiplied?
It's
over
step squared.
step squared added to the original step.
Yeah. So first step would be 1, second would be 4,
25, 36.
49, 64, 81. How could we make that better? I mean, it started wrapping around. I mean, it did pretty well for a while, right? We ended up with 1, 2, 3, 4, 5 good steps before we started wrapping around. How could we make that better?
Bigger array.
Huh?
Bigger array.
Yeah, but we could probably be more precise than just bigger, right? This has got 10 in it, right? And we were able to go 5. This has 11 in it. So let's start at 4 here. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Start at 4, then we would check here. Then next one is 1, 2, 3, 4. And then after 4 comes 9, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36. That one failed. 37, 38, 39, 40, 41, 42, 43, 44, 45, 46, 47, 48, 49, 50, 51, 52, 53, 54, 55, 56, 57, 58, 59, 60, 61, 2, 3, 4. And 64 becomes 81. 5, 6, 7, 8, 9, 7, 1, 2, 3, 4, 5, 6, 7, 8, 9, 81. But 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. Same amount. Why? Prime numbers work better. And, you know, powers of 2 are going to, they're all basically divisible by 2, right? So you certainly want your hash table size to be odd, because that's going to help you get the furthest away. And prime numbers are by far the best. So you want your hash tables to be prime. And then there's a formula that the optimum size is like some number plus 3 is still prime, that kind of thing. But so you have to worry about the size, you have to worry about the function, you have to worry about probing, that's a lot of worrying going around in this. But when done well, man, it's as good as it gets. And basically, you're looking at a big old 1 if you do it right. All right, let's build an open address hash table, because there's a couple things that we didn't talk about, but we need to. let's say we decided to delete 413 from the table. Ta-da, 413 is removed. Now we go searching for 634. We go here and go, oh, there's nothing ever done. It's not in the table. Oops. Huh. So we need to be able to say that this guy was previously used. So now if we go to 634 and go, oh, it's previously used, okay, check the next one. Oh, there it is. If they've never been used, then we'll label them as never used. This previously used comes in really important, because without it, you can't delete from the table. You kind of want to be able to delete from your table. All right. Build one of these days. The chain one's pretty straightforward. I mean, if you build the open address one, you should be able to build a chain one by yourself. It shouldn't take a lot to do that. Here we go. Close this one. Open a new one. What? I'm just going to steal this from a class I did before. I think everybody's like me. Alright. What's the reading card? 342, let's go back 1 year from now, which means it'll be right around the same time. 17th of April. That looks good. What's in here? Probably be searching, I think. Yep. Open address hash. Ha! Look at that. Ooh. All right, we're just gonna steal this code. Actually, I'm not really stealing it because I wrote it, right? Here's our array hash. Let's take a look at the driver for this guy. Yeah, we're just going to steal all of that. Because that way we can just talk about it. All right. Okay, well, delete. I gotta save this first. Save it. Now we go back here and add probe. There's no delete in there. Huh. All right. We'll have to write the delete. That's cool. So need a search. Cool. All right. So in this table here, we're going to set. We have an integer array, and we're going to set the never used to be -1 and previously used to be -2. When we first set one of these guys up, the first thing we want to do is we want to set the entire table to never used. Because Nobody's ever used any of those entries yet. Here's our hash function. It just returns data mod table length. Pretty straightforward. Here's our add. So what happens? We get the data, we get the location by hashing that data. We go to that bucket and we see if it's never been used or it's previously used. Yep, we just store the data in that location. Otherwise, there was a collision. Now, in the case of this one, we're going to probe that location. But you see, we're probing based on the location. So probe equals loc of probe. And so our probe, in this case, is just location plus 1 mod table length. Which, what kind of probing is that? Lindsay. And that's pretty much how we add. Now, how we search is different. So we're going to have to write the search. All right. So to search, what happens? We need to get a hash function to see if the data is there. Then we have to probe to see if we can find it until we hit a never used. If we hit a previously used, we got to still keep going because that means that something was deleted from there and that previously used value was written into the table at that location. So let's take a look at that. Public int. We do want to name, don't we? Table search. Can return either. Let's make it an int. All right, public int search. In the case of ours, we want to search for a certain piece of data. What are we doing here? It's going to look a lot like what happens in the add, right? As we're going to search, we're going to get our location first. There's our location. Then what we're going to do is say if table subloc is equal to data, return loc. Which, you know what? The more I think about this, I don't want to return a location because you shouldn't know what the location is anywhere, and we'll just return a Boolean. And in the case of this, we'll just return true, which will tell us that it does in fact exist there. Now, if it doesn't, we need to probe to find it. And in the case of this, we probably just steal this code here because this is a linear probing, and because it's linear probing, if you wrap all the way around the table from where you are, you didn't find it. So this helps if the table is full. If the table is empty, we will stop when we hit a never used. But if the table is full, we're going to wrap all the way around and we'll have either previously used or datas, and this will help with that. So we find our next location. If the location is equal to never used, that means we're done. But let's try this first. If table subloc is equal to data, return true. We found it. Otherwise, if table is equal to, let's just write them all. If table subloc is equal to never used, what does that mean? If we're probing and we're searching for something, we're probing and we come across a bucket that says never used. So, yes, it doesn't exist in the table. keep searching. So we're in the middle of a for loop, right? What's the easiest way to keep searching? Continue. We get out of the for loop, which means we went all the way around the table, didn't find what we're looking for, we just return false. That's our search. What do you think? The probe takes care of that. Because if we look at the probing method, it mods by table. So that handles the wrap. So linear probe.
So the other table is what? The length of the array?
Yes, the length of the array.
Yeah, it's not going to be present.
Now, that's everything in there. If we save this, we should be able to go back here and now search for that. The search works. The delete didn't. So let's see what happens if we run this. What do we get? Here's what our table looks like. We printed it out there, and we printed out false, looking for 27 plus 31 plus 31 plus 31 plus 32. There. If we put that back to 31, what does it do? Yep. All right. So what happens is we add 27, then we add 27 plus 31. And the reason we do that is it causes a collision, because the table length is 31. So 27 plus 31 plus 31 will also add this will collide, this will collide, this will collide. And the reason we do that is when we look at the table now, that shows that we have those collisions. 27, 58, 89, and it wraps back around to the beginning. The reason we just add 31 is a lot easier than just doing the math. Right? We know the table length is 31. Adding 31 to it's going to force a collision next time it comes by. And this prints out the table pretty nicely. But notice how there are no previously used. So in order to fix that, we would need to have a delete. So in order to write a delete, it's going to look kind of like the search, but if the search returned a bucket number as opposed to a Boolean, that would be awesome. Well, maybe the right way to do this then is public Boolean search int data. It's going to yell at me. You got two things with the same signature. I know. Return search data, and we'll call this internal search. Not equal to -1. Alright, so we'll change the name of this guy then to be internal search, and we'll make him return an integer, and he will return, in this case, the location, in this case, the location, in this case, he will return, you know what? Why don't we do this? Instead of using -1, why don't we just do this? Yeah, this is just a search.
So if you delete a search, does not create a problem?
No, because if we're searching, it'll skip over previously used ones. This is just a return value. That's just a, I mean, we could do this. I don't know, minus. And then what we can do in our search. Be a little clearer now. So we just fail, and we return fail, and in this case, we return internal search not equal to fail. If we go back and run this like it was before, you'll see we still get the true at the bottom there. But now what's really cool is that in order to do a delete, all we have to do is this. Public delete int data int bucket equals internal search for data. If bucket not equal to fail, table sub bucket equals previously used. There. And get off of there. And we can decide what we want to do with this. Sure, we'll make it a boolean. Now we're going to delete. Pretty straightforward. One of the nice things about a lot of these abstract data types is your earlier functions can be utilized by you to make more complex functions. In this case, we search for it and return a bucket. If the bucket's not equal to fail, all we need to do is set that location to previously used. And we're pretty much done. That's it. In the event that it was equal to fail, we return false. And that's pretty much it. I mean, if we can now, in theory, go back to the driver code and comment out this delete, and then it will print the table. And if you look, you can see location 30 there is previously used. So what were we getting rid of? So originally we had 27, 58, 89, 120. So we got rid of 120, which would be 27, 27, 58, right? 27, 58, 89, 120. Yay! So that's a pretty small, but functionally complete hash table.
Data is like key here, right?
Yeah, in this case, data is the key.
There's no value.
Right. The value is the key. Normally you have a key value pair. In this case, the key equals the value. Why don't you take 5, come back, see if I can't hunt down an old chain hash.